So we ended with looking at mechanisms, trying to write out the overall reaction, and identifying intermediates and catalysts if there were any. And so we're just going to do a little bit more of that practice today. And then we're also going to write rate laws based on mechanism. So that's all we're doing today. So we're going to start off with a practice FRQ. So I would like you to take a moment and just do parts A and B on this, where you're going to write out the balance. Actually, we'll do this one together, and there's a couple more we'll practice. You guys will practice on your own. So kind of as a warm-up, it says write out the balanced equation for the overall reaction. Well, the balanced equation for the overall reaction, you will get rid of the things that are, oopsies, on opposite sides of the reaction arrow. So N2O2 is gone, and N2O is gone because they cancel. And then things on the same side get added together. So we have two NOs, and we also have two H2s as reactants. And then on the product side, we have N2 and then two H2Os. And that's it. Now, just like any normal reaction, a way to kind of check and maybe make sure you did it right is everything should balance like normal. So I have two nitrogens on the left, two nitrogens on the right, so that balances. Two oxygens on the left, two oxygens on the right, four hydrogens on the left, four hydrogens on the right. Okay, so everything's still good. It should still, even though we're doing like weird stuff with reactions, they should still balance like normal. Okay, and then this part B asks you to identify intermediates in the reaction and to explain your reasoning. So you can't just identify them and not justify. So intermediates, obviously they're telling you that there are some. It says identify intermediates, and they even told you that they kind of hinted to you that there's more than one because they made it plural. So remember from last time, an intermediate is a substance that is produced and then reconsumed. Now, so far, we've had them be produced and then consumed right after in the next step, and that is often the case, but I just want to kind of let you know that isn't always the case. So sometimes they could be produced in a first step and not used again until a fourth step. It's still an intermediate, though, but more often than not, they are produced and then consumed right after. So I see N2O2 as one of them. It's produced and then it's consumed. And then I also see N2O. It's produced and then consumed. And that would be my justification. They're produced and then consumed in a subsequent step, and you do not see them in your overall reaction. Questions? Okay, that's not too bad, right? So let's do some more stuff. Now, we've been looking at mechanisms. This is obviously like a fake mechanism in the sense that these aren't real chemicals. These are just letters, but we're doing this as just a practice. And what this is showing is now we're going to write a rate law. So we're going to talk about the speed of the reaction based on a mechanism. So in this chapter, there will be two common ways we write rate laws. This way that we're learning today, and then next week, we're going to use data to write a rate law. Both ways are acceptable ways, just depending on what they give you. It's pretty obvious this is a mechanism because I see a bunch of steps and I don't see a data table with numbers in it. So this is going to be the original way we learn how to do it. Now, if your first step is slow, which is what this says my first step is slow, you write the rate law based on your slow step. It's super easy, okay? Why do you write the rate law based on the slow step? Well, if that step is slow, it determines the rate of the reaction. Like you can only go as fast as your slowest step. So your slowest step is going to determine the rate of the reaction. So that's who you write your rate law based off of. And if you remember from last time, whenever you go to write a rate law, the first thing you do is write the word rate. Oh my goodness. Do over. And then you write the equal sign. The rate of the reaction equals rate law constant K, always. So when you go to write a rate law, you can write these three things every single time automatically. Rate equals K, and we'll talk more about K later and next week, okay? And then you find your slow step, which is my first step, and you go, well, how do you know? Well, because I tell you. So it will be written on there which step is slow and which step is fast. How do they figure out which step is slow and which step is fast? They do the experiment. There's no other way to figure it out. It's experimentally determined. But like on a test, I will have to write slow, fast, whatever. Otherwise, there's no way to know which step is slow and which step is fast. And remember, the rate or the speed of a reaction depends on reactants. How fast a reaction goes is going to depend on who you have to start with. So you're never going to see products in a rate law, okay? So W. So you write brackets, which means concentration of W. Boom, that's it. That's a rate law. It's not more complicated than that for when your first step is slow step, which is kind of nice, right? Now, because there's one W, what you would say is the reaction is first order because there's one W with respect to W. And now you're not going to understand orders beyond that today, but next class you will. So all I need you to understand is if there's one of these guys, it's called first order. And we'll learn more in detail what orders mean next class period. So just for now, if you see one of them, it's first order. Now let's just pretend. If there was a 2 up here, it would be called second order because there's a 2. Okay, and again, we'll talk about what those exponents or those orders mean in way more detail next time when we start doing math with them, okay? It looks like I had a question. Give me one second. The standard for slow and fast are just relative to each other. So there is no like set number, but they literally time it with like a stopwatch. There's no standard, but they're the slow, fast. This is relative to each other in the reaction. So this guy's slow might not be might be a different reaction's slow because reactions proceed at different rates. So again, this slow, fast are relative to this specific reaction. You're welcome. Okay. So let's go back to practicing. It says, in the following mechanism, determine the overall reaction, which is what we did last time, the catalysts, if any, or intermediates or intermediate, if any. So let's go to the old stuff, and then we'll write a rate law, which is what we're learning how to do today. So you go, okay. To write the overall reaction, we cancel out things that are the same, or I'm sorry, that are on opposite sides of the reaction arrow. So NO3 is a product and then it's a reactant. So it cancels. So you don't see it in your overall reaction. And then one of the NO2s cancels because you have it as a reactant and a product. It's kind of like think about it like with money. If I give you $2, so think of there's two NO2s in the first reaction, right? If I give you $2 and then you give me one back, your net amount is $1. So that's the same concept with chemicals. You put two chemicals in, you get one out. The overall net is only one of them. So the overall reaction is already written, right? So look, I have NO2 left. I have CO. I have NO, and I have CO2. Notice the K constants, they're a little bit off. They're supposed to be above the reaction arrow. So K1 just means the rate law constant for the first step. K2 just means the rate law constant for the second step. Because remember, if they're going at different speeds, they'll have different rate law constants. Is there a catalyst in here? And now this is where it gets tricky. Remember, a catalyst goes in and comes out unchanged. And so at first glance, it kind of looks like NO2 could be a catalyst because it goes in and comes out. But you need to remember that catalysts do not participate in the chemical reaction, and NO2 is a reactant. So it cannot be a catalyst in this case. It is an actual legitimate reactant, So even though it looks like a catalyst in its behavior where one goes in and one comes out, it's not actually a catalyst. And we'll get to an example later where you see a real catalyst and you can you'll understand the difference hopefully better if you're not sure right now. However, there is an intermediate though, right? There's a substance that is produced and then consumed, and that is NO3. It is produced in the first step and then reconsumed in the second step. Okay, so now we have to write a rate law. So determine the rate law. So I find my slow step because that step determines the rate, and I write rate. Rate equals K. And then I focus on my reactants of my slow step. So NO2, sorry, I kind of ran out of room. NO2. So if I kind of like revise this, simplify it, it would be rate equals K, and then NO2. Geez, this is not going how I would like. And then you would just put a 2 up here because there's 2 of them. So if we're talking about orders, we would say it's second order with respect to NO2. And again, we don't know anything else beyond that. Yeah. So what if there's 2 different elements in the reactants? So do you put them into separate brackets? Yep. And we're going to do a bunch of practice with it today. So the question was asked is if there's elements in different brackets, like if this wasn't an NO2, let's say it was just an O2, you'd have the NO2 in brackets, and then next to it in brackets would be O2. So you'd have both of them in there, but because they're not the same thing, you wouldn't combine them. Great question. Well, it looks like I got another question. Okay, yes. So Mika, yes. This is a good question. This was a commonly, or something that kids were struggling with last class. The catalyst does not participate in the chemical reaction, which is why you don't see it in the overall reaction. So you go, well, how does it not do that? Well, what it does is it provides a pathway for the reaction to happen, but it doesn't actually change chemically. So it's not part of the chemical reaction. It helps make the reaction happen, but doesn't react. So that's a very, very good question and a very important concept to understand, which is why you don't ever see catalysts in your overall reaction. They cancel out. All right. So let's do another one. Let's determine the overall reaction, if there is a catalyst and if there is an intermediate. So let's see. Okay, so this is what I got. 2N2O makes 2N2 and O2. And notice it still balances 4 nitrogens, 2 oxygens, 2 oxygens. All right. Catalyst. I do not see a catalyst in the reaction. I don't see anything that goes in and comes out unchanged. So this reaction doesn't have a catalyst. I do see an intermediate though. This guy, monoatomic oxygen, is produced and then consumed. So that's an intermediate. And again, notice you don't see monoatomic oxygen in your overall reaction. And now we're going to write a rate law. So you find your slow step because the rate of a reaction depends on the slow step, and you write rate equals K. And this is my only reactant in my slow step. So this is the rate law. Rate equals K times the concentration of N2O. That's it. So this one says, consider the reaction of nitrogen dioxide and carbon monoxide to produce nitrogen monoxide and carbon dioxide. And now, instead of them giving you a mechanism, what they do is they give you a rate law and they want you to make up a mechanism. So we're going to practice this together. Remember that their mechanisms, there isn't always like one. A lot of times there's alternate ways you can do it. So if you remember back, we already have done this one. So I'm going to just flash back to it real quick. Right here. It's right here. This was a proposed mechanism, okay, that followed the rate law. Rate equals K, concentration of NO2 squared. Okay, so now we're going to try to make up our own. All right, fine, we will. So I'm going to practice this with you. So we need, oh shoot. We need the rate law to look like this, because it said so. And our overall reaction is NO2, CO makes, ooh, what's the product? I already forgot. Is it NO? NO and CO2. Okay, the easiest way to do this for now, because we haven't learned any other way, is always make your first step the slow step, because it's very easy to write a rate law based on that step. So if you need your rate law to look like this, you need to have your slow step have 2 nitrogen dioxides in it. So I'm going to do step 1 is NO2 reacts with NO2 to make, and I'm going to call this my slow step, because right now, if I write a rate law based on this step, it will look like this. Now, just like in any other chemical reaction, you can't like start throwing carbons over here. You can only have 2 nitrogens and 4 oxygens total if you are going to react just these. So you go, okay, how can I do this? Well, the way they did it in the other mechanism is they put NO over here because that helped get you a product of NO. And then they put NO3 because they needed to get the other nitrogens and oxygens in there. I'm going to just show you another possibility. What about if I did this? 2 nitrogens and 4 oxygens. Okay. Now, I just made something that's not in my overall reaction, so I better get rid of it in the next step, right? So, again, I'm making this up as I go. I'm kind of just like playing around with elements. Now, I know I have to have carbon monoxide in my overall reaction, so I'm going to throw it in there. And I also know I better get NO and CO2 out, so I better put those here. And then look what happens nicely. I have 2 NO2s right now, and I don't want 2 NO2s. I only want one of them. So I have to get an NO2 out so that I only have 1 left. And now let's count elements. 2 nitrogens, 2 nitrogens. 4 plus 1 is 5 oxygens. 1, 2, 3, 4, 5 oxygens. A carbon, a carbon. Okay. Is this possible? Sure. How do you know it's right? You don't, right? The only way you would know if it's right is if you actually do the experiment. So both of these are possible mechanisms for this reaction that match this rate law. What does it mean by slow step and fast step? It means when you do the reaction part, if there's more than one step, some of the part of the reaction happens faster and some of it happens slower. And they like use a stopwatch to time it. Okay. This is not common, but I do want to show it to you. If I gave you this reaction, I said this is the overall reaction, and I don't give you any sort of mechanism to support it, and I don't give you like slow steps and fast steps, and I say write a rate law, you're kind of stuck. Because if I don't give you any other details, the only way to write the rate law is based on the stoichiometry of the reaction, which is a horrible way to write a rate law. However, the only time that the stoichiometry matches up with the rate law, unless it's a coincidence, is if the reaction truly happens in one step, like the reactants go straight to products. These are very uncommon reactions. But if this is all I give you and I say, hey, write a rate law, then you have to do this. You have no other choice but to do this. Rate equals K. Here's my reactants. So you'd put hydrogen in brackets and you'd put bromine in brackets and you'd call it a day. Now, what I mean by the stoichiometry is if, let's pretend, this isn't true, but let's pretend there was a 2 in front of the hydrogen, that would go up as an exponent. If there was a 3 here, that would go up as an exponent. This only happens, unless it's coincidence, when a reaction is single step, which are rare. Single step reactions aren't very common. Most reactions have stuff that happens in the middle. So you will very rarely be asked to write a rate law without any additional information. Usually they also give you a mechanism, which is what we've been doing, or they give you a data table, which is what we will do next week. They very rarely give you a reaction and be like, hey, write a rate law. It's usually followed with something else, because if you write it based on just the overall reaction, you are making a big assumption that the reaction is only happening in one step. Okay? So if you look at this, so we would write the rate law like this, and then you go, oh, the study shows that this is the true rate law, okay? Which doesn't match what we just wrote, meaning this reaction doesn't really happen in a single step. But if I don't give you any other info, that's the only way you know how to do it, okay? Again, this will not be common. What we've been doing is what will be common to write a rate law. So let's do another one. Now, here's the problem. When the first step is not slow, you have to do more work. So we have this mechanism, step 1, step 2, and the first step is fast and the second step is slow. We'll talk about equilibrium in just a second. This double arrow does mean equilibrium, okay? The K1 means the rate law constant for the first step, and K minus 1 just means the rate law constant if you're going backwards, the other way, okay? And we'll talk about the equilibrium in a second. But given what you know, let's determine the overall reaction. Let's see if there's a catalyst, and let's see if there's any intermediates. So let's just do that first, and then we'll go ahead and do the rate law. So it looks like NOBr2 is an intermediate. It is produced in the first step and then used in the second step. And it looks like we end up with 2 NOs and Br2 and 2 NOBr. Okay, so that matches. I don't see a catalyst. Now, based on what we've been doing, how would you write the rate law? Well, you find the slow step. That's right here. And you would write rate equals K. Now, I'm going to call this K2 because it's technically the second step now. And you would do it based on your reactants in the slow step. So that would be NOBr2. And there's a problem. And this is why it's harder when the first step is not slow. Anybody want to guess what the problem is with the rate law? Who is that guy? It's an intermediate, right? What do we know about intermediates? They're unstable, they get used and then consumed. So if you're trying to figure out the rate or the speed of a reaction, having an intermediate in it is not going to be helpful because it's not part of the overall reaction. So what I'm saying is you're not allowed to write rate laws that have intermediates in them. And generally in this class, if your first step is fast and your second step is slow, you almost always have an intermediate in your rate law. And so you have to do some extra work. Okay? You don't get to do this. So you go, well, then what do I do? So you can keep this guy. NO is part of my overall reaction. So you go back up to the first step. Okay? And you go, okay, what does equilibrium mean? Equilibrium, by definition, is the rate or speed of the forward reaction equals the rate of the reverse reaction, meaning it goes back and forth and back and forth and back and forth at equal rates. So maybe it's fast, maybe it's back and forth and back and forth and back and forth, or it's back and forth and back and forth, but at the same rate. Okay? So because the rates are equal to each other, you can write rate law for the forward reaction and a rate law for the reverse reaction and set them equal to each other. So what would the rate law be for the forward reaction? It would be rate equals K 1 NO and BR2 if we were to go forward, right here, equals the reverse reaction, which is K minus 1. Well, if I'm going reverse, this is now my reactant, right? I'm going backwards. So the rate of the forward reaction equals the rate of the reverse reaction. So you set the rate laws equal to each other. And now this is my intermediate right here. So you just solve for the intermediate, which in this case just makes you move this guy over, right? To isolate the intermediate by itself. Now, I do want to show you, this isn't in this problem, but sometimes there's other substances over here than just the intermediate. Like if there's a CO right here, something wrong. Oh. Is it okay now? Okay. If there, this isn't over here, but if there was something over here with your intermediate, you would have to get rid of that guy also. So that guy would also come over here, okay? It's not here, but I'm just showing you everything so you can isolate the intermediate by itself. So now what? Well, my original rate law was this. I think, right? NOBR2 and NO, that's my original rate law. Yep, that's my original rate law that I wrote until I discovered there was an intermediate in it. So now that you've solved for the intermediate, all you have to do is plug this in for the intermediate because we solved for it. So now we say instead of NOBR2, we know NOBR2 equals this. So now you throw all of your K's in. It's kind of like a smorgasbord of K constants. And then NO and BR2. Now, don't forget though, this guy's still here. You can't like drop that guy off. So don't forget to put that guy also in there. So I'm going to simplify this. Now, they often just take this and instead of writing all these little K's out, they call it K prime, which just means a bunch of K's. And then there's two NOs. So I'm going to write NO and then I'm going to put 2. So it's second order with respect to NO and then BR2. and this is the rate law. So when the first step is fast, you write the rate law based on the slow step, but then you have to get rid of the intermediate in it. So it's a lot more work. Okay, we're gonna do more practice with this. Any questions before we do another practice? Okay, let's try another one. These slides right here are just everything I just did, just worked out for you. All right, so here we go. Here's this reaction. Show that the mechanism is also, so this is a different mechanism for the same exact rate law we just did. This is a different proposed mechanism, and we're going to prove that this is another possibility. And sorry, my formatting is a little bit off. So like the K2 should be, I guess it's better when I do this. Here's your K2, here's your equilibrium, okay? My first step is fast, so I know I'm going to probably have to do a little bit extra work. So this is a different mechanism. So let's go write our rate law based on the slow step, like we would normally do. So it's rate equals K, and I'm going to call it K2 because technically it's the second step. N2O2 and Br2. And then I notice that, N2O2 is an intermediate, so I'm going to have to do more work. So what do? I go back up to my fast reaction. And I say the rate of the forward reaction equals the rate of the reverse reaction, because by definition, this is what equilibrium is. Okay, so I write my rate law going forward, and I set it equal to my rate law going backwards. So going forward, it's K, and then let's go back to the reaction. So it's NO and NO, forward. Oops. And then going backwards, it's N2O2 as my reactant, because you'd be starting from the product side in that sense. Again, isolate your intermediate, which is this guy, which does not require much effort. Okay, and then you go, oh, well, I just solved for my intermediate, right? I solved for it up here. So instead of having my intermediate in my rate law, which is unfortunately right here, I'm going to have this stuff. So it's rate. So I just throw all my K's together. And then NO and NO go in for, oops. Okay, so I just took care of this guy, my intermediate. But don't forget, you still have this guy here. So simplified is rate equals smorgasbord of K's. So I just call it K prime. It's like K with an apostrophe kind of thing. And then I combine my NOs, so there's two of them, and BR2. Oh, look, it matches the other one. It's the same exact rate law, different mechanism. Which mechanism is the right one? I don't know. You have to do the experiment to find out which mechanism is the right one. So both are acceptable is the point, and they both match the rate law, and they both are possible outcomes of that reaction. It's not necessarily super hard, it's just harder than when the first step is slow. It's more work. So when you don't really, okay, so first of all, you don't really get rid of the K's. You just, they call them K prime. I mean, you can rewrite the K's as K2, K1 over K minus 1, but really what they do is they just try to simplify it and say K prime meaning a bunch of rate law constants combined, okay? You don't have to do that. You can leave this as K2, K1 over K minus 1. That's totally fine. And yes, the overall reaction will always have you canceling out any intermediates and any catalysts if there is one. And you cannot ever write a rate law based on an intermediate, which is why when the first step is fast, you almost always have an intermediate in your rate law, and it takes more work. Okay, so I would like you to take a couple of minutes to please do this FRQ on your own. So the first two parts are prior knowledge that we've already gone over, and part C is what we're doing today. So they give you a fake reaction. Obviously, they're just using letters, not chemicals. And they ask you a couple questions. So I'll give you a second to please go over that. All right, so the first question asked two factors that determine whether a collision between molecules will occur. So the first the first factor is they need to be lined up correctly. So they have to be able to like collide and lined up correctly. They also have to collide with each other with enough energy, something like that. How would decreasing a temperature affect the rate of the reaction? Well, if you decrease the temperature, the molecules move slower. If they move slower, they don't collide as frequently, and if they don't collide as frequently, they don't make products as frequently, therefore it slowed down the reaction. And then write the rate law. Unfortunately, we have a fast first step, so that makes our rate law a little bit complicated. So you write the rate law based on the slow step still, and then you go, oh no, there's an intermediate in here. So you go back up to your first step and set the two rate laws equal to each other, because the rate of the forward reaction equals the rate of the reverse reaction because it's at equilibrium. That's represented by like the two-way arrow. And then solve for the intermediate and plug back in for the intermediate. So you get rate equals smorgasbord of K's, A, B to the second power. So it's second order with respect to B and first order with respect to A. Any questions before we keep going? Yeah. What would happen if there's like a catalyst? Does that like affect the rate law? It could be in the rate law, yes. If there's a catalyst, it could be in the rate law. Because we know catalysts can mess with the speed of the reaction, right? That's actually what they do. So yes, it could be. We probably won't see many like that, but it is possible. Good question. All right, so try this one too. I don't want you to do D yet. We're going to do D together, but please try to do A, B, and C on your own. So just more practice. Ooh. All right, so the balanced equation would be ozone plus oxygen makes two O2s. That is because the ClO should cancel. Oh, and so should the Cl. Clearly identify the catalyst and the mechanism. Well, chlorine is definitely the catalyst. Why? Because it goes in and it comes out unchanged. Clearly identify the intermediate. The intermediate is ClO because it gets produced and then consumed. Okay, ABC done. Now we haven't done much with units yet, so we're going to kind of do a little quick jump ahead. We will eventually be working with numbers, but for right now, let's just focus on units. So the units for rate most of the time in this class is change in concentration over change in time. So concentration is molarity, and usually the time is seconds, but it could be minutes, it could be hours. But so change in concentration over change in time. So let's compare that to like everyday rates. So like the rate at which you drive, also known as the speed, we measure in distance over time. That's miles per hour, right? But we're not driving a car, we're doing a chemical reaction. So that's why it's concentration over seconds. It's the change in concentration over time, right? So reactants should lose concentration over time and products should gain concentration over time. And then remember, all these brackets mean concentration. So concentration in here is molarity. So if you have a rate law, which is rate equals K, and they told you it was 0.3, and, oops, oh, Carissa. Who's in the rate law? A catalyst, yeah. It's Carissa, right? Okay, Carissa and 2, right? Okay. So rate equals K. Here's what they said. So eventually next week we'll be plugging numbers in, but for now let's just mess around with units. So I just said rate is molarity over seconds. So molarity over seconds equals K, rate law constant. And then the concentration of ozone's units will be molarity. The concentration of chlorine's concentration of chlorine will also be in molarity. So, and now I just rearranged to get K by itself with just units. So I divide both sides by these M's, right? And if you remember, I told you the College Board is obsessed with the units for the rate law constant. And the reason that is because they aren't always the same. You can't memorize them. And I'll show you why in a second. Let's just get through this first. So one of the molarities will cancel. Now be careful, you have seconds on the bottom and you also have molarity on the bottom. So you can either write it like this, 1 over molarity times seconds, or seconds times molarity. It doesn't matter the order. They're both in the bottom though. Or I do need you to be able to recognize, because more often than not, it's not written like this. You can write it like this, but more often it's written like this. M minus 1, meaning the minus means it's in the bottom. And the S minus 1 means the S is in the bottom, right? Because X to the minus 1 is the same thing as 1 over X. So now we're just using units instead of X's. You don't have to write it this way, but I need you to recognize it this way. So you can write it either way, but more often like on tests and like on worksheets and stuff, you're going to see it more often written this way, okay? Now, when I say that the K constant units always change and you go, well, how come they're not always this? Well, what happens if it's like not first order with respect to ozone? Like what if it's second order? Well, then you have M what? Squared. That's going to change your rate law constant. So that's why they like asking you what the units are, because it's not a unit you can just memorize. You have to be able to work out the units based on the order of the reaction. And we'll do tons of practice with that next week when we get to the math part of this. Okay, I think there was one more question. Oh, I skipped the overall order. Well, if it's first order with respect to ozone and first order with respect to chlorine, it's second order. You just add them together. So what does that mean? Well, let's pretend. Let's pretend it was second and second order. It'd be 2 plus 2. So it would be fourth order. You just add them together. It's not too bad. And then what is the rate determining step? Well, if this is the rate law, remember, the rate law is based on the slow step or the rate determining step. So does your rate law match any step? For the remember, it's based on the reactants. Look at your first step. If you were to write a rate law for the first step, would it match what this is if it was the slow step? Right? So if this was slow and you were to write a rate law based on it, this is what it would look like. So obviously your first step is your slow step. If your first step doesn't match your rate law, then by default the second step would have to be slow. I mean, you don't have any other choice. Okay. Oh, sorry, I have a question. The first part of D, you mean the overall reaction? You just add the exponents. So this is an invisible one. This is an invisible one. So 1 plus 1 is 2. That's how you do the overall. I'll do a random one. if it was third order for ozone and second order with chlorine, the overall order would be 5 because 3 plus 2 is 5. Okay. All right. So I apologize to my second period. For some reason, we went, I think it was because I had issues with the pear deck starting so slow. We didn't get to this, so please pay good attention. My third period got to this, and we'll be able to finish this. So potential energy diagrams we've already done before, but we've only done them as one step. So like in this class so far, when we've done potential energy diagrams, they look like this or like this, right? And it's just one big hill you have to get over. It's called a potential energy diagram. Well, when it's just one hill, it's assumed to be a one-step problem. And the thing is most reactions aren't actually one step. So now we're going to look at a potential energy diagram that kind of shows you that there a reaction that has more than one step. So if you look at this, there's a bunch of hills. However many hills there are is how many steps there are. So step 1, step 2, step 3. It's not really that much harder. Remember at the top of the hill, we have what are called activated complexes. What they are, I keep using this word smorgasbord. That's not very chemical-like. What they are is just a smashed up version of these two guys. In this instance, there's two reactants. Of these two reactants together, they're not like a real thing. They're them colliding with each other, right, to get to be able to make products. So they're not like a super stable thing. They call it an activated complex because it's not really a real chemical. It's like them just being all thrown, smashed together, stuck to each other until they can make products. So the things that happen in between, intermediate, intermediate. And then again, the beginning and end are the same. These are my reactants. These are my products. And this kind of stuff just happens in the middle. So what we're going to do is we're going to practice, excuse me, we're going to practice looking at a sample mechanism without chemicals, but with actual numbers, energies, and just answer some questions that we know for a multi-step mechanism as opposed to a single step. So I have this 3-step mechanism. Oops, I guess I shouldn't have said that. We weren't there yet. I have these 3 hills, okay? It's obviously more than one step because I see multiple hills. So I'm sorry, I'm going to have to keep flipping back and forth because my questions are on the next slide. So this mechanism has how many steps? I already said it, right? It's 3. Why? Because it has 3 bumps, 3 hills. Remember, EA stands for activation energy. So the activation energy for the overall reaction will be from the reactants to the tallest hill, the one that's hardest to get over. So reactants, which are here, the beginning of the reaction, to the tallest hill. So that's here. That's my biggest hill. So here to here, 50 to 80 is going to be 30, right? So 30 kilojoules is my activation energy. Which step is the rate determining step and which step is the fast step? So I don't know, you tell me. If you're trying to climb up these hills, who's the hardest hill to get over? The second one, right? So the second step is your rate determining step. It's going to take the longest to get over this hill. It's the hardest, it's the biggest hill to climb. So so step 2 is your rate determining step, but your fastest step would be your shortest hill. And it definitely looks, it's close, but it definitely looks more like step 3 is a little bit shorter than step 1. So step 3 would be your fastest step. So step 2 is the rate determining step, and step 3 is the fastest step. And the overall reaction is what kind of thermic? Well, remember the exo endothermic is defined by delta H, right? So if it's positive, we are endothermic, and if it's negative, we are exothermic. But just conceptually, without even doing math, your products have more energy at the end. So energy had to have been absorbed for you to have more energy at the end than you did at the beginning. So that's endothermic. Okay, so this is an endothermic overall process. Oops. And now delta H is, by definition, products minus reactants. So, looks like my products are trying to say are at about 70, right? Minus my reactants start at 50. So 70 minus 50 products minus reactants is what delta H equals. So that'd be a positive 20 kilojoules. Now, what's delta H for the reverse reaction? Reverse means if you were to go backwards. So if you were to go this way, it's now 50 minus 70, right? It's the same number, just different signs. If a reaction is endothermic one way, it is exothermic the opposite way, and vice versa. So it's the same number, just opposite signs. So it's negative 20. That means this much heat would be released, lost, given off if you tried to go backwards. Activation energy for the reverse reaction. So just like the forward reaction, except for if you're going reverse, you're starting at products. Now, it's the same thing where you go products to the biggest hill to get over. It's still the second one, right? The second hill is still the hardest to get over, even going backwards. But now at my products, I'm starting at 70, and the biggest hill from there is up at 80. So up here, so here to here, is about 10. So going backwards, it's 10. In other words, it's easier to go backwards in this reaction than it is to go forward. And then again, the rate determining step for the reverse reaction is still the second step because it's still the biggest hill even when you're going backwards. Okay. Any questions on a potential energy diagram that just has more than one step? A catalyst would appear at the beginning and the end, yes. But this is a great question that I didn't get asked. How could you show a catalyst is present? A catalyst will not change your starting or ending point, ever. However, it will lower your activation energy, so you would see shorter hills, okay? So like, let's just do a single step. Looks like this, right? The presence of a catalyst would have the same starting spot, but an easier hill to climb. Same ending spot. Remember, by definition, catalysts lower activation energy. Okay. So, speaking of that, catalysts do not change in a chemical reaction. They go in and come out the same. They lower the hill. They make the hill easier to climb, which is why the reaction goes faster. Okay, they speed up the rate of the reaction by lowering the activation energy. And like in biology, we call catalysts enzymes. So like lactase is an enzyme or a catalyst that helps facilitate the breakdown of lactose, which is sugars that you find like in dairy products. So people who are like lactose intolerant are lacking enough of the enzyme to break down the sugar. So those are biological catalysts. Now in this class, we have different kinds of catalysts, and they're not supposed to be confusing. I don't know why this is always confusing for kids. A homogeneous catalyst is a catalyst that's the same exact state of matter as its reactants. A heterogeneous catalyst is a catalyst that's a different state of matter than its reactants. Okay, so again, catalysts will lower the activation energy. It does not change anything else. Delta H stays the same. Reactants start the same. Products end the same. Just the hill is easier to get over. Okay. So look at a homogeneous catalyst. So this is the demo I was trying to do till someone jacked my hydrogen peroxide. So hydrogen peroxide breaks down super slowly. Like you can go buy a bottle of hydrogen peroxide and you could stare at it for hours and like nothing's gonna happen. You don't really see this happen in real time. It does do it, but just very slowly under normal conditions. So if you add a catalyst, like sodium bromide, and it's specifically the bromide ion. It's not the sodium just floats around and minds its own business. The bromide ion speeds this reaction up, and you actually can see it'll start like bubbling, right? Because you're going to get oxygen out of it. So it'll start bubbling really, really quickly and start breaking down. Now, the bromide is considered a homogeneous catalyst because hydrogen peroxide is aqueous and the bromide is aqueous. They're in the same state of matter. That's all that it means. The catalyst and the reactant are the same state of matter. Okay, whereas, we're going to talk about real quick the catalyst of like ozone, the destruction of ozone, like with chlorine. So this is like a fairly slow process, no catalyst. Okay. However, with a catalyst like Cl, it happens much faster. It lowers the activation energy. And you always go, well, okay, if ozone is being converted to oxygen gas, why is this so bad? Because oxygen gas isn't bad, right? We breathe oxygen gas. So those Cl atoms, right? Cl atoms, and again, it's a homogeneous catalyst. Why? Because it's a gas, and ozone's a gas, so they're the same state of matter. They come from like Freon and all those things that like that they try not to use anymore, like in refrigerants and things like that, because they get released in the atmosphere and they break down the ozone. And you go, well, so what? It just turns it into oxygen, and oxygen's not bad. Well, the thing is the ozone absorbs horrible, like the UV rays from the sun. So we want the ozone. It's not that we don't want the oxygen. It's that we need the ozone to help absorb the harmful rays because, right, we know UV light is damaging to us, right? It damage plants, animal life. It can damage our skin. That's why we wear sunscreen. So the less ozone molecules that are in the atmosphere to absorb those rays, the more they come to us. So again, it's not that the product of ozone breaking down is harmful because it's oxygen gas. It's that we don't want that. We want to keep the ozone because it's helpful to us. A lot of people think that like, ozone, I don't know, usually you think, oh, what it turns into is bad. We don't want the thing that it turns into because it's bad. And that's, in this case, sometimes it is bad. Sometimes when things break down, they do break down into harmful things. In this case, that's not what's happening. It's the UV rays that are harmful. We just want to keep the ozone to help protect us from the harmful rays from the sun. And look how crazy this is. Each chlorine atom, one monoatomic chlorine, will kill or destroy 100 ozone molecules. That's how damaging it is to the ozone molecules. That's how quickly it turns those ozone molecules into oxygen gas, depleting the ozone layer, really, okay? A heterogeneous catalyst. So look at this. This is iron. This is just saying iron. Iron, we know, is a solid, right? It's a metal. And this is the Haber process where they take nitrogen and hydrogen to make ammonia. And this is, it is important that they speed it up. Ammonia is a main component in fertilizer. And what do we use fertilizer for? Like basically everything to like grow crops, our food sources, right? Things like that. So they try to make ammonia fast. And they do that by using an iron catalyst. And the iron allows the nitrogens and the hydrogens to bind quicker to make the ammonia. Now, this is considered a heterogeneous catalyst because nitrogen is a gas, hydrogen is a gas, and iron is a solid. So it's a different state of matter than the reactants it's working with. That's it for heterogeneous and homogeneous. You know this from biology. So look at, you've got some substrate, okay? And it binds right here, and it usually binds because of some sort of intramolecular forces that attract it, right? And you've got this substrate, and then the enzyme comes in, or the enzyme, and it breaks it apart, takes the substance you're trying to break apart and make new stuff. So you've got like lactose, okay? Or lactase, lactose comes in. Here's the lactase. Here's the lactose, breaks the lactose down so that it doesn't hurt your tummy, okay? Again, that's another example of a biological catalyst, okay? And also known as like the lock and key model. We just kind of talked about that. Okay, I know that class is going to end pretty soon. Yes, I got through this more faster than I thought I would. So could you, it says, we're just doing this part. It says, consider the 4 reaction energy profile diagram. 1, 2, 3, 4. It says, identify the 2 diagrams that could represent a catalyzed and uncatalyzed reaction pathway for the same reaction. Indicate which 2 diagrams, and you need to indicate it. It doesn't even say justify it, it just says indicate it. So if you're going to, pick 2 diagrams, you should have the same starting and ending spot if it's for the same reaction. Because a catalyst does not change your reactant's energy or your product's energy. It just helps get you there faster. So who would we say? I'm going to go with 1 and 2. They start at the same spot. They end at the same spot. One's hill is just lower. And then, so right, if you like superimpose this curve right here, diagram 1 on here, it would look like this, right? If you try to superimpose it, stick it on top of it, it's the same starting and ending point, but a lower hill. So diagram 1 would be the catalyzed reaction, and diagram 2 would be the original reaction. These guys don't have same starting and ending points, so they're different reactions. And this last thing says, indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. Adding a catalyst to a reaction, make sure it adds energy that causes a reaction to proceed more quickly. Careful. Part of the statement is true, right? Adding a catalyst causes a reaction to proceed more quickly. But what by how? How do catalysts make a reaction proceed more quickly? They lower the activation energy. They don't add more energy. They lower the activation energy. They provide an alternate pathway for the reactants to mix or react. They don't actually add energy. So I disagree with the statement because catalysts cause the reaction to proceed more quickly by lowering the activation energy and providing an alternate pathway for the reactants to react.